Welcome to MET 200 Manufacturing Processes and Material. In this lecture, I will be talking about metal alloy and their structure. In this lecture, I will be speaking about material mostly, and material is very important in manufacturing processes because it's the material that is going to be transformed, and it is the behavior of material when it is subjected to particular force, temperature, for example, and other physical parameter that will determine the success of operation. Certain material respond well to certain type of manufacturing processes, and some of them will respond poorly. So in this lecture, we're going to be talking about characteristics and property of material that determine their capacity to be transformed by different manufacturing processes. As you already know that all matter are made up atoms, and atoms consist of nucleus, proton, neutron, and surrounding cloud or orbits of no electron. Many of physical property of material that are predicted are based on the knowledge of the interatomic forces that bind these atoms together. Here we have two figures. The top one force, and this is energy, which is corresponded to two atoms, two isolated atoms, and these two isolated atoms are brought into very close proximity from very far separation or infinite separation. And the top side of this figure shows attraction, and the bottom part shows repulsion. And each atom exerts some force on the other atom. But at this very infinite separation, we see that interaction is negligible. Once they become closer to each other, we see some attraction and repulsive force, and that magnitude is a function of separation or interatomic distance. Why we have attraction, or why we have repulsion? The reason is that when you have two atoms, the center nucleus has a positive charge, right? And the outer shell, which are electron are located E, they have negative charge. This is another atom. When you bring these two atoms together, initially we have more attractions, because this electron is attracted to this nucleus, which is positive, right? This attraction increases, but at a certain distance, this electron and the electron on the other atom will create repulsive force. And the same thing happens with this two nucleus. So that's why we get repulsive force when we are when we have this atom too close to each other. At a certain area, we have a state of equilibrium. That is the location we have a minimum energy. Here, the definition of an ion and cation is here for you to review. As I mentioned before, matters are consisted of atoms, and atoms are held together in a molecule by various type of bond. We have two type of bond, for example here, primary bond and secondary bond. primary bond is associated with the formation of molecule, and secondary bond is associated with attraction between molecule. Keep that in mind. A primary bond is much stronger than secondary bond. As I mentioned before, we have the primary bond, which is stronger than secondary bond, and in the primary bond, which is characterized by atom-to-atom attraction, involves exchange of valence electron. Depending on the way the electrons are going to be shared, we have three type of bonds. One is called ionic, and then we have covalent, and then the third one is called metallic. And this schematic shows these three types. In the next slide, I describe this bond individually. The first bond is called ionic bond, as I mentioned before, and this type of bond involve exchanging the valence electron in order to increase the electron count in the outermost shell to provide number 8. Why 8? Because 8 electron in the outer shell is the most stable atomic configuration, and nature provides a very strong bond between atoms that achieve this configuration. So what happens, this element, this metal, transfer electron to this atom, and then this atom will have 8 electron in the outermost shell, and this one which was a giver gets a plus sign, and the other one which is a receiver gets a negative sign. One example of ionic bond is table salt, where we have a sodium chloride and NaCl, and we have Na, which is sodium, and chlorine is Cl negative, and they are strongly attracted to each other, and property of solid material with the ionic bond is that they have a very low electrical conductivity, and they have a poor ductility. The next bond is called a covalent bond, where the electron is going to be shared between two atoms. This is the opposite of the ionic bond, where the electron were supposed to be transferred from one atom to another, but here the electron is going to be shared between two atoms, and in that case the outermost shell will achieve a stable set of 8 atoms, 8 electrons. In the covalent bond, we have two examples, fluorine and diamond. In the fluorine, we have atoms that are two atoms that are going to share the electron, and 2 electrons will be sharing, and then the fluorine atom will get 8 atoms in the outermost shell, and it will reach a stable configuration. But in the case of a diamond, the atoms, for example this one, is going to be sharing electron with the four neighbors. This is one, this is another, the third one, and this is the fourth one. So after that, they will reach stable configuration, eight atoms. So electron, no solid that has covalent bonding, they have a very high hardness. Hardness is hard, high, and the electrical conductivity is low. You can imagine how hard the diamond is. It is just because of the covalent bond it has. The next type of bonding is called metallic bonding, and this type of bonding occurs in pure metal or metal alloys, and the atoms of metallic element has very few electron in the outermost shell. That's why the electron are going to be shared in the entire block, so they call it general electron cloud. And this type of bonding provides some good characteristics. For example, good electrical conductivity, good conduction of heat, and good ductility. In this course, we will be talking mostly about metal, and that's why these characteristics are very important for us to keep in mind. Later on, we will address this characteristic more in detail. Back to metal. It's important for us to answer some questions. Once we answer this question, then we can use them as a guide to predict material behavior and material characteristics in the manufacturing processes. For example, why some metals are soft and why some of them are hard, and why some metals are brittle and why some of them are ductile. If we want to answer this question, how are we going to answer this question? We have to study the atomic structure and arrangement of atoms. Once we understand this structure and arrangement, then we can answer these typical questions. Why metals are important in the manufacturing processes? There are unique properties that are associated with metallic bonding. That some examples is high stiffness and strength, and they can be alloyed, so to provide high rigidity and higher strength and hardness. One example is steel. Steel is an alloy of iron and carbon. Their toughness is very high. So toughness means capacity to absorb energy. So if you have a higher toughness means the capacity is going to be higher, so you will absorb more energy with that material, which is a metal in our case. And the electrical conductivity in metal is very high. That's why they are being used in industry as a conductor. And the thermal conductivity is also well known in the metal. They have a very high thermal conductivity. And cost, if we look at the cost, the price of the steel, for example, one metal, one alloy in this case, is very competitive with other engineering material. Here we describe the structure of solid material. When material solidifies from molten state, they tend to pack tightly. In many cases, they pack themselves into orderly, structure. For example, like this one, as you see, we have a dense and regular, packing, and then in some cases they are, random. So we don't have a dense packing, or they call it, non-dense, and they call it, amorphous or non-crystalline. In metal and some of ceramic and some of polymers, we see crystalline structure under normal condition. When a metal solidify from a molten state, the atoms of metal arrange themselves into orderly configuration, and the smallest repeating part is called a unit cell. And we have different type of unit cell in metals. Some of the important and some of the well-known unit cell are here for you. One is called face-centered cube. I explained this in the next slide. For example, one material that has this type of unit cell is aluminum, and then iron is gamma iron. I explain what is gamma iron later on. Silver, nickel, copper. These are some of the metals that has this type of unit cell. The next one is body-centered cube, BCC for short, and chromium and tungsten, vanadium. These are some examples of material with the BCC structure. And hexagonal close packed, or HCP for short, in this category we have zinc, zirconium, cobalt, and magnesium. The first crystal structure is BCC, body-centered cube. In this slide you see three figures, but all of them are indicating the BCC structure. And this is one material, and the smallest repeating part is this unit cell. And if we take it out here and show it with this schematic, we see that one atom is located on a corner. If we want to so this definition is important, how many atoms are within this unit cell. So then it provides some information about the packing factor, atomic packing inside the unit cell. So if the numbers are high, means you have more atoms inside the unit cell. So let's these coronal atoms are shared with the other unit cell. So that's why we are considering 1/8 of that atom, right? And then we have a similar behavior here, 1/8 here, 1/8 there. So we have totally eight atoms inside this unit cell, which 1/8 of them are within the unit cell. Okay, and then we have one entire atom inside or within this unit cell. So if you want to calculate the number of atoms in this unit, is going to be 8 times 1/8 gives you 1 plus 1. So the number of atoms inside this unit is 2. The next crystal structure is called face-centered cube, or FCC for short. In this unit cell, similar to BCC, we have atoms on the corner and then one atom on the face. Since if we want to calculate the number of atoms within this unit, we can multiply 6 by half, because half of these atoms is inside this unit cell. The other half is shared with the other unit cell. Plus, we have 8 corners, and each corner we have 1/8. So that gives us 4 atoms. 4 atoms assigned to this unit cell. So as you can get some idea, the number of atoms in this unit cell is more than the previous BCC. That means more atoms are inside in this unit, and the packing factor, the atomic packing factor, is larger in BCC. This is one characteristic. Later on we use it a lot when we want to describe or justify a behavior in metal. The next crystal structure is called hexagonal closed packed, or HCP for short. In this unit cell, we have 3 planes: top, middle, and the bottom. On the top plane, we have 6 atoms on the corners, as you see here, and 1 atom on the center. The same thing is going to be repeated on the bottom, the lower plane. But in the middle, we have 3 full atoms within the unit cell. If we do some simple calculation, we can find that the number of atoms within this unit is going to be more than any other unit cell we described, FCC and BCC. For example, we have 3 atoms, right? 3 full atoms, 3 times 1, and this atom, half of it is going to be shared, half of it is going to be inside this unit. So 2 plus 1, because 1/2 of 1 on the top surface, the top face, and 1 on the bottom face. So by now we have 4, right? If we combine them, we get 4. But we have these corners. If we do calculation for this, definitely it's going to be more than 4. So FCC had 4, and BCC had I think 2. So HCP has more atoms inside the unit cell among these 3 units we explained here. Here we have 2 definitions which are important, material study. One is called polymorphism. It happens in solid material that have more than 1 crystal structure. For example, steel, carbon steel, can have a BCC structure as well as FCC structure. It depends on temperature and pressure. And allotropy is another definition. In some material like carbon, they have a similar chemistry, but their physics and their physical are going to be different in different conditions. For example, carbon can exist as a graphite or diamond. Here, this picture, we see a structure, the crystal structure of carbon steel, which varies at different temperature. Carbon steel or pure iron up to 900 degrees Celsius has a BCC structure. After that temperature, it will transform to FCC structure. Then it is stable until 1391 degrees Celsius. Again, after that temperature, we see a BCC type, BCC structure, and then around 1536 degrees Celsius, it will transform to a liquid. And this characteristic, this type of behavior, we call it polymorphism. Other important definition in material study is single crystal and polycrystal material. When metal cools from molten state and they begin to solidify, the crystal, individual crystal, as you see here, will nucleate at a random position and orientation. For example, this was formed here, the other one was from here, and these crystals grow, and finally they interfere with each other as temperature drops. Finally, we see grain. Grain means once the material cools completely to solid, then we have this interference between different orientations. So each part is called a grain. If you have a material that has no single orientation, you just have one repeating unit, repeating pattern, it's called a single crystal. But if you see material that has a grains like this one, then it's called polycrystalline material. So it means it has so many grains in it. Many of material that we discuss in this course are polycrystalline material, but there are some engineering applications that require single crystal. Single crystal means a single grain. One example can be diamond single, and in this material is used for abrasive application. The next one is turbine blade, which uses single crystal structure. Inconel is one material that is going to be used for this application. And the reason we use single crystal for this application is that it reduces the creep failure. Creep is one failure that happens in at high temperature. So when you use single structure, single crystal structure, the tendency to have creep failure is going to be reduced. As I mentioned before, polycrystalline material have many grain in it. This is a very beautiful image taken by SEM microscope, scanning electron microscope, one type of microscope that can magnify the part by high magnification factor. As you see here, this is a part that was welded. Different color means different grain, and here near the weld we have a larger grain further out, further away from the weld. The grains are smaller compared with in the weld zone, this area. You may ask that how we can distinguish, the grain under a microscope. When we look at, the part, first you have to, polish the sample, and then you see, grooves, surface groove between, grain here. And then under the optical microscopy, because the orientation of each grain is different, the light that is going to reflect back has different angle. As you see, the angle is different. That's why you see, this coloration. What are the mechanical properties of single and polycrystal? The single and polycrystal, they have different mechanical property that we should be aware. For example, property in the single crystal vary. They vary with direction. It means the property is anisotropic. It's not isotropic. It's not the same in all directions. And one example is this unit cell that is showing the Young modulus. Young modulus is one mechanical property that we can obtain in the tensile test by pulling apart, a dog bone sample. When you stretch, this dog bone, then you see a stress, a strain behavior like that. Up to some point, we have a linear behavior, and the slope of this is called elastic modulus. If one material has a higher modulus, means that material is harder, so the slope is going to be higher, so it's harder to stretch, so the elongation is going to be less. So here we see that along Young modulus in one direction is 125 gigapascal, means 10 times 10 to the power of 9, 1 to 5, 10 to the power of right. And let me erase this part. And this one is 273 times 10 to the power of 9. So Young modulus in this direction is larger than the other direction. It means it's not isotropic. In the polycrystal, because the grain are located, they are formed randomly, so the size is going to be the size of the grain are going to be random, so the property is going to be isotropic, and in all direction you see similar Young modulus. For example, this is the Young modulus of iron. Okay, this is an example of a metal or iron that was a stretch. If you put this iron in a roller, then the metal or sheet metal is going to be stretched in one direction, because it's stretched in one direction. The atom or grain is going to be stretched along that direction, and it gives you an isotropic property. So the size of the grain are different in different size, in different direction, right? So this is important. Rolling is one of the mechanical, one of the manufacturing processes that changes the property, and you see, anisotropic property. Grain size has a major, impact on the mechanical property of metals. For example, at a room temperature, the larger grain size means that lower strength, or lower ductility, or lower hardness. If you are interested in having higher strength, then you have to change the process parameters in a way that it gives you a smaller grain size. For example, the grain size is inversely related to the cooling rate. If you change the process parameter that in a way that you see a faster cooling, then you should be able to have a smaller grain size. Normally grains are very small to see. You have to use a microscope, and until if you want to observe the size of the grain. But sometimes depending on the process parameter, they can be so large that they can be observed with the naked eye. The yield strength, which is, as I said before, a mechanical property of material, can be obtained by a formula that is a function of initial yield strength and the grain diameter. The grain diameter is D here, and K is the constant, which is dependent on the material. If we want to quantify the size of the grain, we have to follow the ASTM, American Society for Testing and Material. As you see, there is an equation here. N represents the number of grain in inches squared when it is magnified by 100x, and then you plug that number into this equation, and then you will obtain this number, which represents the size number in ASTM. Here is one example to find how many grain we have in a paper clip. The paper clip is made of wire that is 120 millimeter long and 0.75 millimeter in diameter, with a ASTM number size, ASTM grain size of 9. So what is the number of grain in this paper clip? First, we need to look at the grain size of number 9, which is here, and the grain how many grain we have in meter cube is 1000. No, 185,000. Right? And then we need to find the volume. Volume is pi over, pi over 4 times d squared times L. We know diameter, which is pi over 4 and 0.75 squared times the length is 120. Which gives you 5.3 meter cube. So if we want to find out how many grain we have to multiply the number of the size by volume, right? So if you do that, then you get 9.8 million. It's a large number, right? In a paper clip, which is a very small size, you have about 10 million grain. Okay, what is non-crystalline or amorphous structure? Non-crystalline or amorphous, they mean the same. And water, air are some of the non-crystalline structure, and we don't discuss this material in this course, but it's good to know that once the metal transformed to liquid, then it becomes amorphous or non-crystalline. Glass or many plastic or rubber, they are categorized in a amorphous shape. There are two important features of non-crystalline structure. One is that they don't have a long range repeating order, or the configuration is not repeated, and they have differences in melting and thermal expansion. A couple takeaway from this lecture: metals, when they are in the solid state, they have a crystalline structure, and we have BCC, FCC, and HCP unit cell in the metals, and the atoms are held together by metallic bonding. Because of the metallic bonding, we have highest strength and hardness, high electrical and thermal conductivity. FCC unit cell provides good ductility, which are important when we are looking at the manufacturing processes such as rolling, forming,